Okay, so you can see share the screen.
Yes, sir.
Okay, so here we briefly discuss about the relevance of the results that we have seen for hydrogen atom to a more general case of many electron atoms. So essentially, we would like to ask a question: how we can understand the periodic table, the arrangement of these atoms as uh, they are in the periodic table. But please understand that this was done by many chemists and many people even before they know anything about the structure of atom or discovery of electron, etc. Purely by just looking at the pattern, trying to understand the pattern. Okay, so that in itself was a very interesting experience to understand. Okay, so it is an interesting thing in itself to understand how such conclusions are drawn, but that is a separate historical study. So, so let us say that we have a typical mini electron atom. Okay, so there are Z electrons and Z protons. Z protons and Z electrons. Of course, Z neutrons are also there, but I am not bothered because they are not electrostatically active. So now if I want to write down a Hamiltonian for such a many electron atom, I will have to write the following Hamiltonian. The Hamiltonian is given by H is equal to. So let us say that I have sum over um, so let us assume that uh, the nucleus is at rest. Okay, so I have Z number of electrons and each of them has its own kinetic energy, twice m the electron mass. And each of the electron will interact with the nucleus, and that is going to be sum over I is equal to 1 to Z. And this minus sign is because ZE is the charge of the nucleus, E is the charge of the electron, so ZE square by Ri. Okay, Ri is the distance between the nucleus, and the nucleus is like a point mass. Okay, it is a fixed center. Okay, Ri. Then there is a term which is the interaction between the electrons. So which you can write it as sum over I is equal to 1 to Z and sum over J is equal to 1 to Z. And interaction between the two electrons is given by E square divided by modulus of Ri minus Rj. This is the electron-electron interaction term. Now in this double count, double summation, each pair is actually counted twice. I mean each pair is counted twice. So in order to compensate for that, so I will have to put a factor of half here. Okay, so some double counting is done. So here, so assume nucleus is a point charge of charge at of charge ZE, okay, and located at the origin of coordinate system. So this is something which we are modeling. Okay, so this is an assumption of our model. Now, if you make this assumption, then this is going to be your Hamiltonian. Now, the problem here is that in general, so let's say you have Z number of electrons. So you have to solve. So you want to get the energy levels of this atom, then you have to solve this many particle Hamiltonian. So this H, and then you have a psi. This psi will depend on R1, R2, etc., Rz, because there are Z electrons. That is equal to E. It will depend on, of course, so many quantum numbers, and right now let's not worry about that. So R1, R2, etc., Rz. Okay, and this problem as such is not exactly solvable. So this is not exactly solvable. Solvable even for helium atom. And what is speciality of helium atom? Helium atom is Z is equal to 2. That means there are 2 electron atom. Even for that, this is not exactly solvable. And why this is not exactly solvable? Because of the presence, of uh, interaction term, that is electron-electron interaction. Electron-electron interaction, which is kind of a two-body term in the Hamiltonian. If you see, first term and second term will depend only on I. Only this term will depend on I and J. That is the meaning of saying it is a two-body term. Okay, so this is what it is, and so one way to look at is, okay, shall we get rid of this one? That means shall we neglect this electron-electron interaction? That is one option, but then you will see, to neglect that one, it should be very small compared to the other terms, right? So that is one aspect. So ignore. So first option is, option 1 is ignore electron-electron interaction. Okay, so let us try to understand how wise is this option. So for that, let's consider helium atom. So consider helium atom. Okay, so in the helium atom, you are going to have this Hamiltonian. For this is going to be P1 square by twice ME plus P2 square by twice ME minus 2E square by R1 minus 2E square by R2 plus E square by, I will call it as R12, where R12 is modulus of R1 minus R2. So this is the Hamiltonian for helium atom. Now if I neglect this, so let's neglect this. So if I neglect, this is like, I can write this as H1 plus H2. Now each of this Hamiltonian is like a hydrogen atom Hamiltonian. The only difference is in hydrogen atom, the nuclear charge is plus E, here it is plus 2E. And we have discussed in the last class, if you have hydrogen-like atoms with the nuclear charge as Ze, then E square will be replaced by Ze square in your uh, in your energy. That means each of this energy will become, wherever E square is there, you have to put 2E square. But in the energy expression, so for hydrogen atom, the ground state energy E1 is equal to minus me e to the power 4 by 2h bar square, which is equal to minus 13.6 electron volt. Now what happens is that this particular E, so for helium atom, single electron, so this E1 is going to be equal to minus me. Instead of e to the power 4, I have to take Ze square the square, and Z is equal to 2 in this case by 2h bar square. That means this will be 4 times 13.6 electron volt. Okay, and we have 2 electrons. So we have 2 electrons in helium atom, and those 2 electrons will not know that there is other electron because it is not interacting with each other. So the energy, the ground state energy of helium atom will be equal to, so this is for 1 electron, for 2 electronics it is 2 electrons, it is double of this one, so minus 8 into 13.6 electron volt. Okay, so this will be, so minus 108.8 electron volts. Okay, so that is what will be the ground state energy of helium atom. But you can ask whether this is our theoretical estimate by ignoring the electron-electron interaction. Okay, so this is by neglecting electron-electron interaction. Okay, so it turns out that you can one can do an experiments. Okay, so you can do an ionization experiments. From ionization experiments, it was found that the ground state energy is around minus 75 electron volt. minus 74.8 or something like that. So it's a minus 75 electron volts. So you can see that there is a large difference, about 30 electron volts of difference between what we have estimated and what experiments have found. So that means it is not a wise option to ignore electron-electron interaction, even for helium atom. Okay. So what is the second option? Second option is uh, so option 2 is treat electron-electron interaction as a perturbation. Even though we did not discuss perturbation, but here the idea is I'm not going to do the calculation. So I'm just trying to say that if I have to use this perturbation, that means without this term we solve this problem exactly, and then use this term to correct for those energies. Okay, first order perturbation, second order perturbation, you can progressively incorporate corrections due to this term. But one of the requirement for this to be a viable method is that, okay, so for perturbation, for the perturbation theory to work, we require the perturbation term to be small compared to unperturbed term in the Hamiltonian. Okay, so now what we do is we will try to compare how small is this term compared to uh, the term which is already there. So let us go back to our general Hamiltonian. That is, let us consider a Z electron atom. And here we will make one assumption. Okay, so we make this following assumption. Let's make an assumption that that Ri and Rij are of same order, are same magnitude, are of it's not same, kind of a similar magnitude. Okay, and what is the justification? Justification is because of electron repulsion. Since electron and electron are repelling each other, they will try to push them apart, so that distance between any two electrons for all I comma j. So distance between any two electrons will be of the same order of magnitude as the distance from the electron to the nucleus. So this is something which is reasonable to assume because there is an electron-electron repulsion. Now, once we make this assumption, then what you can see is that uh, there are so so the magnitude. Okay, so the magnitude of this term, that is sum over I is equal to 1 to z, z e square by r, ri. This term can be said that this will be of the order of z square. Okay, this will be of the order of z square because this is proportional to z and there are z terms. So you can pull this out, then there will be z. So that will be of the order of z square. Now, let's try to understand what is the magnitude of this term. That is half sum over I is equal to 1 to z, sum over j is equal to 1 to z. Okay, so E square by Rij. Okay, so now if you choose first electron as I equal to 1, second electron can be 2 to z. And if the first electron is 2, then the second electron is 1 to z other than 2, and so on. So this will be uh, half of z into z minus 1. Okay, this will be of the order of z into z minus 1 by 2. Okay, so now let us define um, some quantity which is basically the ratio of these two interactions. So let us define something, I call it as rho, which is ratio of the magnitudes of these two terms. That is half z times z minus 1 divided by z square. Okay, so which is equal to z minus 1 by 2z. Okay. Now this has to be, so why am I calculating this? For perturbation theory, to work, this rho has to be much smaller than 1. That means the if I were to use electron interaction as perturbation, then it should be much smaller than the electron nuclear interaction. Okay, so that is the requirement. But then we can see here that so let's say for helium atom, what is z is equal to 2. So your rho is equal to 2 minus 1 divided by 4. So that is equal to 1 by 4. Less than 1. Okay. Uh, now suppose if z is very large. Okay, suppose if z is very large, that is for large z, what happens? For large z, you can see that this 1 can be neglected, z minus 1 can be neglected. So rho is equal to half. Okay. And for example, you take for lithium atom, where z is equal to 3, rho is equal to 3 minus 1 divided by 2 into 3. Okay, so that is equal to 1 by 3. So you can see that this is less than 1, but far from being able to realize that this is much less than 1. And hence, in all likely, that perturbation theory will not work. Okay, it is not possible to, even the option 2 is not a very good option. Okay, so we can see later, that perturbation um, together with variational method gives a reasonable estimate for the ground state of the helium atom. Okay, so this we will do as an exercise for perturbation theory and variational calculus. But anything other than helium atom, uh, even for lithium atom, you can see it is 30%. That means it's not small, so you cannot use perturbation theory. So we require some new idea. So this is not what is going to work. This approximation is not going to work. Okay, so what one does, what people tried and then succeeded was they made something called so this is what is called central field approximation. Central field approximation. Okay, so the central field approximation is something like this. You write down your Hamiltonian. So the Hamiltonian of many electron atom in this approximation is, so I'm going to write down the Hamiltonian sum over I is equal to 1 to z pi square by 2me plus sum over I is equal to 1 to z. So let's say I have a Vi of Ri. Okay, so I will call it as VIC of Ri plus some W. Okay, so here VIC of Ri is the central potential seen by ith electron nucleus as well as other electrons. Okay, so this is in some sense is like some mean or effective field. Effective field seen by ith electron. Important is that it is central. That means it depends only on the magnitude of the Ri. Okay, and what other things are there? There may be some non-central part, and there may be some other interactions. So rest all is um, in the term W. Okay, and in the first approximation, so in the first approximation, we ignore W. So if you ignore W, then it is very So your H can be now written as sum over I is equal to 1 to Z Hi. Okay, so now you see each one is, but the interaction is already present in the central potential. So this is like decoupling. Okay, so where this Hi is the Hamiltonian for the ith electron. So pi square by twice me plus Vci of Ri. So if you solve this equation or the eigenfunction of this equation with eigenvalue, then that actual eigenvalue of this whole Hamiltonian will be sum of the eigenvalues, and eigenfunction is going to be the product of the eigenfunctions. So if you are able to decouple like this, this has a simplifying form for the Hamiltonian. But even though I have written this is the central potential, but do we know what the central potential is? We don't know the central potential. Okay, so but we do not know this Vci of R. This is the problem. Now let's try to understand what this Vc uh, R can be by just looking at our atomic system. So our atomic system has got so the atom has the following. This atom that we are thinking is that we have, let's say, Ze is the charge of the nucleus, and you have several electrons. So one of the electron, ith electron, let's call this as um, ith electron, and then this is your Ri. Okay. So now let's try to ask the following question: that suppose if so first let us look at asymptotically what this VIC should look like. Okay. So now as your Ri goes to infinity, okay, as Ri goes to infinity, then what happens? Uh, this electron, the ith electron, ith electron would see the nucleus with charge plus Ze and Z minus 1 electrons together as a point charge of charge plus E. Why? Because nucleus charge is plus Ze and Z minus 1 electrons charge is minus of Z minus 1 into E. So it will be Ze minus Z minus 1 E. So it will be 1 E. So it will see it as a charge like this. So because of this, what we can say is that this Vi, the central potential of Ri, as Ri goes to infinity, will go to minus E square by Ri. Minus E square by Ri. So this is the form of this potential asymptotically as Ri goes to infinity. On the other hand, as Ri goes to 0, okay, so then what happens? Then the ith electron ith electron would see the complete nuclear charge. Complete nuclear charge. Okay, that is total ZE. So then what you can say is that this VIC of Ri, as Ri goes to 0, should go like minus ZE square by R. Now what happens? What happens in for any finite value of R? For any finite value of R, it has to be something between these two. Okay, so we can see this graphically. For example, if you try to plot, this is your R, and let's say that you have two graphs. One graph like this. Okay, so now what is this graph? So as minus E square by Ri, that means as Ri goes to 0, this goes to negative. So minus ZE square by Ri will be, so let us say this is your so this graph is ZE square by Ri. Let's simply call R, and this is minus E square by R. Okay, so now what happens to the actual form is that it should go like this as R goes to 0, and then as R goes to infinity, it should go like this. Correct? So this is what I would say that is the actual VC of R. Okay, so maybe I should have used a different color. So it starts from here, and then it joins this one. So this will be your VC of R. So it should interpolate between these two things. Okay, it should interpolate between these two things. Now, what kind of a function will this will do this job is at this moment arbitrary, and we have so we have no way of determining that function. Okay, but one can, there are methods in quantum many body theory, and people do a lot of work even just to determine what this central field potential should be. Okay, so one can do some intelligent kind of a construction work. Okay, so for example, let's say that you just want to find an interpolating function. Okay, so this is what you call as modeling. So modeling of this VC of R, okay, that satisfies this kind of a asymptotic behavior. So that is something one can do. And so it is something like this. Suppose let's say that uh, I can write down my VC of R should be equal to, let's say I must have a 1 over R, okay, and then of course there's a minus sign here, and I must have when R goes to 0, okay, then I should have ZE square by R, right? So I may have some function of R here such that when R goes to 0, it should go to minus ZE square by R, and when R goes to infinity, it should become minus E square by R, correct? So one has to think of, so let us say that, so let's say Z is, so even E square I can write here because E square is common. So I can say that uh, Z minus 1 by R. Okay, so if R goes to 0, okay, so let me put it this way, Z, so essentially what I'm trying to do is I'm trying to interpolate this. That is, I have minus E square by R, and then I have some kind of a alpha plus some beta into Z. Okay, so alpha and beta into Z. Now we require as R goes to, okay, this alpha and beta can in principle be functions of R. Okay, so as R goes to infinity, I require beta of R to go to 0. So one possibility is that we can say beta of R is equal to e to the minus R. So that will do this job. And then as R goes to, and what should alpha of R? Alpha of R should go to 1. Alpha of R should go to 1. And as R goes to 0, what I should have is I should have beta of R should go to 1, and alpha of R should go to 0. Okay, alpha of R should go to 0. So that is what I want. So then I can, now let us say alpha of R is R goes to 0, that becomes 1. So this can be written, now I can write this as minus E square by R into uh, yeah, so let me say that Z into e to the minus some constant you can have. So let's say e to the minus alpha R. Okay, so this alpha and this alpha are not same. Maybe I say e to the minus AR. Okay, we have difficulty with respect to all this square by R into Z into e to the minus uh, some capital A into R, and as R goes to infinity, this becomes Z. So Z is square by R, and plus I have, as R goes to 0, this becomes Z, but then I don't want that Z to be there. So I have to write down 1 minus Z here. Okay, so the Z will cancel. It will become minus E square by R. Oh, R goes to infinity, it should be like that. Yes, that is, R goes to infinity, this becomes 0. R goes to 0, I require it to be Z E square by R, correct? So R goes to 0, this is Z E square by R. R goes to infinity, this becomes 0. And so this will not do this job. So Z minus 1 minus Z minus plus Z, it is, so Z minus 1 minus AR. R goes to infinity, this becomes 0. And then R goes to 0, this Z minus 1. 1 minus Z, this goes to 0, Z. 1 minus Z plus Z. Okay. So I think, I mean, please understand that the modeling is always like this. So Ri is equal to minus E square by R into 1 minus Z into e to the minus AR plus Z. So this is my model potential, ARI, of course. Here I put Ri. A is some constant which you can choose as a model parameter. Now notice that as Ri goes to infinity, e to the minus ARI goes to 0. Okay. E to the minus ARI goes to 0. So that means you have, what is that? You should have, as I goes to infinity, it should be minus E square by R, right? So that means, so I must put this as 1. Yes, I think I put this as 1 and this as Z minus 1. Okay, this goes to 0. So you get VC I of Ri is equal to minus E square by Ri. Now as Ri goes to 0, then e to the minus ARI goes to 1. Then you will have this Z minus 1 plus 1. So plus 1 minus 1 will cancel. Then you have this VC of I of Ri is equal to minus Z E square by R. So this is one function. I'm just interpolating this one. Okay, just to say that how we try to figure out some function if you don't know. But now the point is, okay, I have this potential now. Now I have to put this potential in the Hamiltonian and then try to find out the eigenstates. That may also be difficult, but I'm just trying to show you how if you don't know how you figure out or how you start modeling it, how you get some function which has this desired properties of asymptotic behavior. Okay, so that is one function. So the function is, so one of the, so a model function, model central potential with desired desired asymptotic behavior can be constructed as Vc of I of Ri is equal to minus E square by Ri into Z minus 1 e to the minus ARi plus 1. So one can, if you have, so you can solve this. Okay, but this is not unique because I have used one method to construct this. Okay, so this is just one of the model potential. Okay, so this is one of possibly many functions with with such asymptotic behavior. And by by no means we can say this is the correct central potential. Since we don't know, we have some potential, but we cannot say that it is correct potential. Correct potential means it should be derived from the electron-electron interaction and all this. I have not bothered about any of those things. I have only looked at the asymptotic behavior and I have simply interpolated this between those two behaviors. So there is no way that we can say that this is the correct central potential. But we can do something slightly better even if you don't know what this potential is. Okay, so we will try to understand the general issues with respect to this potential. For example, we can ask a question that, so let us try to note several generic behaviors. Okay, so let us note the following general features. So the first one is that your central potential Vc of R is not of 1 over R form because it has to interpolate between minus Jd square by R for R going to 0 to minus E square by R for R tending to infinity. So in between it cannot be 1 by R. It has to go faster or it has to go slower, so it will not be of 1 over r form. So what is the implication of that? Now in hydrogen atom, energy eigenvalues depend only on the principal quantum number n and are dependent of L and M. Okay. Now note that the independence on M is due to rotational invariance and rotational invariance is there because of central potential. So note that the independence of M on M is due to rotational invariance. Okay. Whereas energy not depending on L is is um, is the property that is special to 1 over r nature of the Coulomb potential. In hydrogen atom. Now, since Vc of r is not 1 over r form, the energy eigenvalues depend on both n and L. Just a minute. Okay, so they both depend on n and L. So the in general, we denote ENL. Okay. However, there is no M dependence, because Vc of R is also a central potential. Is also a central potential. This is a general feature. Whatever is your Vc of R, whether it may be the model potential that I wrote or maybe some other model potential that you write, these features that I am going to write are very general. They are actually independent of the actual form of your central potential. Okay, so that is the first conclusion because of the form of this potential. And second is that we have now, you can see that suppose you take let's say you take ENL, okay, and let's say EN prime L, take two energies, okay, so and so let's say N prime L prime be two energies. Then if N prime is larger than N, that implies En prime L prime is greater than, okay, so let us first talk about a given L. Okay, so En prime L is greater than ENL. Okay, so note that here L is fixed. Okay, so this is first, so let us make this is first one. And second is that suppose you have ENL and ENL prime. So here N is fixed. N is fixed. Then if L prime is greater than L, then ENL prime is greater than ENL. Okay, so uh, this is the order in which. And now lastly, suppose you have ENL and En prime L prime. Nothing is fixed. Okay, NL and N prime N prime. N prime L prime. Then if N prime plus L prime is greater than N plus L, okay, if N prime plus L prime is greater than N plus L, that implies En prime L prime is greater than ENL. Okay, so now you have to understand this in the following way. See, if you have, so there is a general rule in quantum mechanics like this. If you look at your one-dimensional problems, ground state does not have a node. First excited state has got one node, second excited state has got two nodes, and so on, right? So that means uh, as you go to higher and higher energies, the number of nodes of the wave function will increase. Or in other words, the nodes of the wave function is proportional to energy. Now, if you say you have ENL So for the wave function corresponding to this psi and L, okay, so wave function has got n, so this n radial nodes, basically these are zeros of radial function, radial nodes, and L angular nodes. These are zeros of spherical harmonics nodes. So the total number of nodes is equal to n plus L. So if the total number of nodes is large, then the energy will be larger. So that is the reason when n and L both of them are changing, then you have to use this what is called n plus L rule. And this n plus L rule is because of the number of nodes. Okay, so this correspondence between number of nodes and energy is monotonic. That means if n plus L is large, then this is also large. Okay, so we have these rules. Okay, and now there is only one ingredient which we have to bring into this in order to understand periodic table. So that is the ingredient called spin. Okay, so this is in some sense one of the best kept secret of the nature, and Pauli had unearthed the secret. And there is this electron has got a spin degree of freedom. So let us try to uh, come back to spin after some time, but for the moment let's try to understand that so electron is a spin half particle and is subjected to Pauli exclusion principle. That means in any energy level, you cannot have more than two electrons. One electron with upspin and the other electron with downspin. Okay, so now with these principles, which are quite general, as I told you, they don't depend on what form of the potential that you have chosen. Now, what is the energy of these energy levels will depend on the form of the potential. But all these points that I have written here are independent of the choice of your central potential. That it is central is important, and that's all that is important. There is nothing else that is important. But actually, you want to know whether it is minus 20 electron volts or minus 25 electron volts. To make a decision on that, you require to uh, get the actual potential and then work with that one. Okay, so now let us try to build this periodic table. So the periodic table is something. So let's imagine that um, we have an energy axis here. So let's call this as energy. And in this direction, let's say we have the principal quantum number n. Okay, so now let's say that we have n is equal to 1. Okay, so let us draw a line like this. This is n is equal to 1. So for reasons that you will shortly know, that there will be two electrons in this. Of course, you know, because of Pauli exclusion principle, there will be two electrons in this. And we call this as 1s orbital, 1s, and there will be 2 electrons. This is n is equal to 1. Now, when you come to n is equal to 2, then so n is equal to 2 corresponds to what? So let's look at this one. N is equal to 1 corresponds to L is equal to 0, and of course M is equal to 0. And there will be 2 electrons corresponding to 2 spins. Now, if you take n is equal to 2, then you can have L is equal to 0, M is equal to 0, and L is equal to 1, M is equal to minus 1, M is equal to 0, and M is equal to plus 1. So there are 4 states associated with that. And so n is increasing, so the energy will increase. So we have uh, this is called 2s, and then for 2p, L is increasing, so the energy is higher. So we have 2p here, okay, and there are 2 electrons here, and there are 6 electrons here, okay. So in this particular case, the hydrogen and helium atom are here, and then of course you have uh, lithium and beryllium, and then you have the 6, and the 6 will be boron, nitrogen, oxygen, carbon, fluorine, and neon. So by this you have all these 6 elements fixed. Now let's go to n is equal to 3. N is equal to 3, we'll have 3s, and so n is equal to 3, as you can see here, we'll have L is equal to 0, M is equal to 0, L is equal to 1, M is equal to minus 1, M is equal to 0, M is equal to plus 1, and L is equal to 2, M is equal to minus 2, M is equal to minus 1, M is equal to 0, M is equal to plus 1, M is equal to plus 2. So these many states will be there, and this state is called 3s, and these states are called 3p, and these are called 3d. There will be 10 such electrons. So this is 3s, there will be 2 electrons, and then you have 3p, there will be 6 electrons, and then you have 3d, there will be 10 electrons. Okay. So this is so this will have sodium and magnesium, and then all this transition. Then you have second list, correct? So uh, boron. So these elements, which are oxygen, phosphorus, carbon, silicon, fluorine, chlorine, and all those elements will come here, and then the transition element, the first row of the 3D block, will come here. Now, if you take n is equal to 4, then so n is equal to 4 and L is equal to 0 and M is equal to 0, that is 4s, right? Now for 4s, note that n plus L is equal to 4. Whereas for 3D, n plus L is equal to 5. So because of that, your 4s will have a lower energy than 3D. 4s will have a lower energy. Then you will have 4p. Then you have 4d. And then of course you also have 4f. Okay. So this 4s will have smaller energy than 3D because of this n plus L rule. And now you can populate. Um, so I think there are elements where instead of going to 3D after 3p6, that means after argon, okay, so you will have potassium and calcium will occupy 4s. Okay, so K and potassium and calcium will occupy 4s than 3D. After calcium only your transition elements will start. Okay, so like this n plus L rule will play a role in other things also, like compared to 4D you have 5s is a lower energy and things like that. So the periodic table can be built in this particular fashion. So I have not used anything uh, specific of the form of this vector potential. Sorry, the form of the central potential. But now there are certain issues with respect to this periodic table. For example, so let's say, uh, so if you take chromium has got an atomic number 24, and that means you have 1s has 2, and 2s has 2, and 2p has 6, and 3s has 2, and 3p has 6. So 10 plus 2, 18, and then 4s2, 20, and then 3d4 it should be 3d4. But this configuration, which we would have written as normally like this, is not correct. Okay, so the configuration, this turns out to be incorrect. Okay, what is the correct one? Correct one is up to this is the argon configuration. So we will write this as argon, and then 4s1 and 3d5. So there will be only one electron in this and 3d5. Okay, so this is because half-filled d shell with one 4s electron, half-filled 3D shell with one 4s electron is more stable. I'm just writing what you would have read in textbooks. More stable than 4s2 3d4 configuration. Okay, but then you have to ask a question: what is it that actually reduces the energy? More stable means what? This will be 4s1 3d5 is having a lower energy than 4s2 3d4. That is why it will settle to this configuration, right? So how is the energy getting reduced? All these rules that I have talked about is not going to help us in answering this question. Okay, so same thing is true with another element called copper. So copper is 29. So we would have written this argon 4s2 3d9. This is what we would have written, but this is not correct. Okay, so this is not correct. But what is correct? Correct one is argon 4s1 3d10. So the argument is same. Completely filled 3D shell with one 4s electron is more stable than 4s2 3d9 configuration. So for these two, and then there are many more like this in the later higher electron elements. So for these things, the energy is lowered, and what is the reason why this energy is lowered, or what? So maybe you have to consider the W, which we have neglected, and that W cannot be neglected in these cases, or maybe there is something more. Okay, so this question we have to address this question from quantum mechanics. Okay, so what what is the mechanism of lowering of energy in half filled and completely filled D shells in chromium and copper. So this question is interesting, and we require to understand the mechanism. So this is one question which, with the quantum mechanics that we have learned so far, we are not able to answer. The second question is more interesting. The second question is, we have something called these inert elements. Okay, so inert elements. They are helium, neon, argon, krypton, xenon. Okay, I forgot what more is there. So these are the elements which are, maybe radon is one of them. So helium, neon, argon, krypton, xenon, these are inert elements. Why they are inert? Because they don't participate in chemical reactions, right? So they are inert. Now, why are they inert? Okay, so we can ask that question. Why are they inert? Okay, so what people tell us is that, okay, it has a completely filled shells. Okay, there are no free electrons to participate in bonding. Okay, so completely filled shells. Now, is this the answer? Now, if this is the answer, then why completely filled D shell is not inert? Okay, so if this is the answer, why completely filled D shell atoms like zinc, for example. Zinc is zinc has an electronic configuration of argon 4s2 3d10, right? So this is next to copper. So this is not inert, and zinc is very reactive. So zinc is not inert. So why it is not inert? Because here also one shell is completely filled, D shell is completely sealed, or F shell completely filled atoms. That is lanthanides and actinides. F shell completely filled atoms. Okay, so the question is, why only completely filled P shell atoms are inert? So this is the question that we are asking, and this requires also some thought. So we would like to answer these two questions, and some more quantum mechanics we have to learn to answer these two questions. But these two questions are right now I am raising because this is something, it's easy to understand the question. Okay, so we would like to ask why this is important, or what kind of explanation can we give from quantum mechanics for this. Okay, so this is in some sense some discussion on periodic construction of periodic table given the given the generic nature of the form of the central potential, and then what conclusions can we draw. Right now you see, if I have to tell you what is the value of this 1s level energy value, then I require to know what is the actual potential. Okay, so there is usually this obtaining this central potential is usually done by using what is called a self-consistent computational method. Okay, so what one does is, of course, you also have to, if I have to describe that, I have to tell you a little more about what is called uh, many particle states and many particle wave functions. Okay, so which is probably we will study that in quantum mechanics 2 next semester, but you have you have to have that kind of knowledge. So I am only choosing to explain it without actually going into the details of that many particle wave function and its properties. Okay, so this is just to say that with this much understanding, what can we do. Of course the questions are there which requires to be answered, and that requires some understanding of many particle wave function. Okay, so this is about how we get to this business of periodic table from quantum mechanics. Okay, so let us try to. So I mentioned about spin in passing. Maybe I say a few. Let me spend a little more time on spin. So the spin. So let's try to understand that you have something called an orbital angular momentum. Okay, so let's say that I have orbital motion or orbital angular momentum. So this is something which we have classically we have understood this, and then we have quantized this. So we have a class. So did I write two times? So orbital angular momentum. So we called it as L, and then we have talked about it earlier. So L, and this is a vector. So maybe I represent it like this: L vector cap. Now, since electron, the orbital motion of the electron. Okay, so the orbital motion of an electron implies a magnetic dipole moment to electron. How do we know? And what is this magnetic dipole moment? We can say that this magnetic dipole moment, let me call it as mu L, is equal to E by twice me into L. So this is the dipole moment. Okay, so if you say that there is an angular momentum L, that means there is a magnetic dipole moment mu L. How do we know? How do we know? If we apply magnetic field if I apply magnetic field, the electron responds to the applied field responds to the applied field as a magnetic dipole, as a magnetic dipole with dipole moment mu L is equal to E by twice me into L. Okay, this is how it responds, and that is how we know. And if you say that angular momentum is quantized or apply magnetic field along z direction, then this is going to be along z direction. Then eigenvalues of Lz operator will become the so you can see that the energy levels etc. will be based on this dipole moment interaction with the magnetic field. Okay, so this is something which we know. Okay, so we have solved one problem earlier where a hydrogen atom is kept in a magnetic field. Then the form of the Hamiltonian that we have seen, that is H1. Okay, that form is something like this, right? It is E by 2 me into Lz when you try to apply magnetic field along z direction. Okay, now supposing if you say that, so that means, so this is something that we know. Okay, so this is something that we know. Now, if we consider some particle which has no orbital angular momentum, okay, so uh, if uh, if we consider an electron that has no orbital angular momentum, we consider an electron that has no orbital angular momentum, then it should not respond to it should not respond to magnetic field, at least as magnetic dipole. Okay, so you may say that there may be higher order multiple moments. It should not respond at least as magnetic dipole. Okay, but it does. It does respond like a magnetic dipole. What does that mean? That means the electron, so electron magnetic moment is not entirely due to orbital motion, due to orbital angular momentum. It's not entirely due to orbital angular momentum alone. There is something else. Okay, so initially people thought that so initially people, predominantly people like this Uhlenbeck and Goudsmith, thought that electron spins about its own axis. In addition to orbiting around the nucleus. Okay, so the story goes something like this. Uhlenbeck and Gauss-Smith, after reading the paper written by Pauli, have this kind of a picture in mind, and they actually calculated and then completed, written their paper. And Uhlenbeck and Gauss-Smith were students of First. So they wrote a paper and then they gave it to First for communicating it to a journal. And then Uhlenbeck actually goes and meets Lorentz, and then Lorentz shows a mistake, I mean, a fallacy in their paper, that if you actually think that the electron is spinning around this nucleus, then if you want to get the magnetic moment to be h cross by 2, which is what is observed uh, in uh, in an experiment by Stern and Gerlach. So if you want to get that angular momentum, then the speed of the orbital speed of the electron has to be larger than the speed of light, which is a contradiction to special theory of relativity, which seems to have no known contradictions in physics. So then Uhlenbeck actually rushes back to Unfirst and says, hold on, don't send this paper. There is a fallacy in that. So Lorentz said that this is what it is. But then Unfirst says, I already sent it. And he says, okay, let us see what happens. But anyway, he says that you people are just young, and you are just in the beginning of your career. So even if it is wrong, you have nothing to lose. I mean, if you have a name and fame, then you do some wrong thing, then you will lose all that name and fame. You are just beginning, you are young students. So you have nothing to lose. Let it be wrong. It doesn't matter. Like that, he says. Okay, so that is how the concept of something spinning around its axis came into existence into the literature. And to a very large extent, even now, I think it is prevalent. Some people try to imagine that something is spinning and things like that. But even before Uhlenbeck Gaudsmith's paper was published, it was shown that such a thing is not possible. So even though this name spin stuck to this concept, there exists no spinning motion with respect to electron. And we don't know that whether electron has got any structure so far. Okay, so there is nothing spinning. So this was so which uh, we have no reason to validate or believe to that matter. So what is the correct understanding? So the correct understanding, in my opinion, is the following. So the correct understanding is electron electron possesses an intrinsic magnetic dipole moment, like it possesses it possesses charge. Before that, people believed that the magnetic moment is a derivable quantity. You have a charge, and charge is something which is rotating about some rotating in some closed orbits, then you get a magnetic dipole moment. So this was what Faraday's contribution is. Faraday said, okay, magnetic moment can be understood as a circulating charge. But now it looks like that magnetic dipole moment is an independent property which need not be originated in the charge. So these are two independent intrinsic properties. So every electron is like a tiny bar magnet. It has its own magnetic dipole moment. And you ask a question that what is the origin of this dipole moment? There is no answer. That the electron has an intrinsic dipole moment. Okay, so this seems to be the correct understanding. Now the confusion further comes because of the mathematics that we do in quantum mechanics. So what we do in quantum mechanics is that uh, so since an angular momentum gives a magnetic moment, a magnetic moment mu L, we assume reverse is also true. That means there is a magnetic moment, which I will call it as spin, and you must be able to talk about an angular momentum operator corresponding to this. Okay, but remember, there is no angular motion. This is just a mathematical angular momentum operator. Okay, so this is mathematical spin angular momentum operator, angular momentum operator postulated. No angular motion is observed with no angular motion ever observed. So it's a mathematical quantity. Now, once you say that, because what is observable is only how an electron responds to the applied field. So so what is observable, or what can be observed, is the response of the electron to applied magnetic field. Okay, so now you can say that there is some, let's say that there is some magnetic moment which is called mu L, and then there is some magnetic moment which is called mu S. Okay, and then you can say that if you apply magnetic field to this, it responds as if it has got a magnetic moment mu uh, which is equal to mu L plus mu S. That means what? You can actually add these magnetic moments like vectors, and then the effective magnetic moment or the total net magnetic moment. So this electron will respond to the applied field as if it has this net magnetic moment. And because of this observation, we can also add this angular momenta at the level of L and S. So you can add L, you can add S, even though L is something which has a physical basis even in classical physics, and S does not have any physical basis in classical physics. S is a mathematical spin angular momentum postulated because of the existence of intrinsic and magnetic dipole moment for these electron fundamental particles like electrons. Okay, so from now on, what happens is you do everything mathematically and get results, and finally you see where that results are being observed in terms of the response of the electron to the applied field. Okay, so this is how the spin is understood, or to be understood, in my opinion. So this is what spin is about. But we have to understand that even though what we are saying historically, this is how it has been discovered, but spin as such is a property which comes only from the relativistic quantum mechanics, because spin naturally comes from Dirac equation. So if you want to understand spin completely, you have to wait till we study relativistic quantum mechanics, and that is the natural way in which spin comes out of quantum mechanics. Right now we are observing in the experiments and putting this spin by hand. Okay, there is a spin operator, this can be added to the angular momentum, and so on and so forth. But the correct representation or correct way to understand spin is from relativistic quantum mechanics, namely the Dirac equation. Okay, so I will stop here. If you have some questions, okay.